Okay, hello. This is the physics corrections for the chapter 2, unit 2 test, And so first we have a few questions that we are going to go over. The first one is this diagram. It's in backwards, so you can get a general sense. There are two blocks here on an incline at angle theta 1 and a mass 3 at an incline at theta 2. And these are the coefficients of friction, just generic terms that we're going to use. And so we have three questions that we're going to go over here today. So let's start with the first one. The first one is the largest M3 for the blocks to stay at rest, the largest M3. So using that, let's take a look at the question here again. So we're just going to go over the free body diagrams first. So for the free body diagrams, we have a normal force acting upward on M3, which is perpendicular to the surface it is on, and mg is kind of at an angle here. Mg is straight down no matter what, kind of at an angle like that. And 3g, just to be more specific, force of gravity. And since there's no acceleration in the vertical, just relative to the incline, there's no acceleration there, so these forces will to Fn. Since it's on an incline, it'll be m3g cosine of theta 2, and this way parallel to the incline is m3g sine theta 2. And so the force acting that way, this force, like that, that's m3 g sine of theta 2. So that has to be greater if they don't want any motion. That has to be less than the forces acting in the other way. So m3 g sine of theta 2. It has to be less than that maximum force of friction, but it has to be equal so there's no acceleration the other way as well. And we also have to, so the same thing is going to be the same for the other forces in the other direction, for M1 and M2. Here. We're just going to treat that as one large mass, M1 plus M2. G sine of theta 1, that's the force of gravity acting parallel to the incline that way. And then we're also going to incorporate the frictional force between them. So between plus, so that's going to be less than plus m1 plus m2 g cosine theta, since that's the normal force. Take up their normal force, theta 1, times the coefficient, the static coefficient between M1 and the incline. Let's see that. We're going to have to use this, the ramp, and this one, since there's no motion, it's static friction. And we're going to use that coefficient of friction there. And then we also incorporate the friction from mass 3, g cosine theta, and that is the force of friction acting on M3 from the incline, times the coefficient of static friction, and the ramp 3. So we can do this, bring all the M3s on one side because you're trying to find the largest M3. So bring all the terms of the M3 to the left side, just simple algebra. say that's kind of messy, but we can simplify that. And M3 and then we can just divide it by that. This is our answer. M3 has to be less than that for there to be no motion. And because that is the forces of friction and the gravity acting in the opposite way. So that's then equal to, so there's no motion because M3 is pulling equally downwards from the gravity parallel to the incline here. M3, this force is pulling down equally as the frictional force is acting here, and thus there is no motion. That is part 1. And part 2, part 2 is asking, now it's the opposite, M3 large enough to cause motion. So it's the same process except M3, the force of gravity acting here, as I showed before, is going to have to be greater. I have to overcome these retarding forces over here so that it will cause motion in this direction, down the slope. So we get, firstly, we get M3G sine theta 2 has to be greater than, and for this we're just going to treat M1 and M2 as one large mass, since there's no movement among the blocks like that from M1 and M2 like that. It's just going to be one large mass. That's, I'm just putting them as a quantity. It says that block 2 does not slip on block 1. So first we get this simple equation. M3G sine theta 2 is greater than M1 plus M2G sine theta 1. And then, so F net equals MA equals M3G sine theta 2 minus and we'll go like that. So if you're just using Newton's second law, F net equals ma, and we're going to solve for the acceleration. So a equals g m3 sine of theta 2. That's the gravity acting parallel to the incline. Force of gravity minus sine of theta 1. Again, gravity parallel to the incline minus and now you see this is the normal force, m1 plus m2 cosine of theta 1. That's the normal force times muse of k2, because it's k now because there's motion, so it's a coefficient of friction, coefficient of kinetic friction against the incline. And then the total mass system is m1 plus m2 plus m3. So just breaking this down, you see the force of gravity acting parallel to the incline is that has to overcome the force of gravity acting parallel to the incline here and the friction here. see that here. And then I forgot one last part. On the numerator, you have minus we just have to add the force again, parallel to the incline of gravity. Then we have the friction here, and then this is the friction that mass 3 experiences on the incline. So we have to look for all of these in this system, and then M3 g sine theta 2 has to be greater than all these forces for there to be motion. Then we just divide by the total mass here, and we get the acceleration due to Newton's second law, F equals ma. Just divide by the mass. And yeah, so that's the first two questions, and now that's the theoretical portion. Basically, we just want to make sure that we understand the free body diagrams and the total. We have to account for all the forces acting on the masses. A good diagram that I drew was actually the here, the free body diagrams. Free body diagrams like that. It's kind of bleeding through the paper here, but you can kind of see when you join forces on an incline, mg is always shaped down like that. But we want to do the forces acting relative to the incline. That's mg sine of theta, and straight down mg cosine theta. And that mg cosine theta is equal to Fn a lot of the time, and the mg sine theta is what's causing the acceleration in the direction that is flowing down the incline due to gravity. Yeah, that is it. And then we'll go over some of the actual we'll go over like this with actual numbers. And I forgot one last part. The second question has no slippage on block 1 and 2, but the third question asks for that 2 slips in 1. So if the tension is pulling like that, that's causing the motion because M3, as you saw before, is pulling like that. It's pulling like that. So the force of friction on M1 from the incline, this is the incline, the dotted line. It's going to be that way. It's against the direction of motion. And but now M2 wants to go this way, opposite, forcing some slippage. Thus, that is the force that it wants to go, but this is the force of friction. And so that is M2 times G. So that's F of n, basically. The M2 faces times the coefficient of friction that we given. If there's slippage, there's going to be kinetic friction of this motion. Okay, then 1 on 2 is 1, just that. And equals F of F. And we can solve for that's the force of friction. We can solve by just simple algebra, solving for the masses and acceleration. And the same thing, the tension minus F of F equals because we're gonna have to add the total masses. See here, when the force of friction acting that way, like in the past parts of the problem, you had to add, combine the masses, and so, times g times, we're going to use kinetic friction, so k, and 2. It's for coefficient of friction given to us. So that is part 3, and now I'll just go over some values. Alright, for the purposes of length for this video, I'm just going to go over the second part using the real values given to us. There's arbitrary values. It's in backwards, sorry Mr. Worth, but I didn't know how to film it without using mirror. But M3 equals 5 kilograms, M2 equals 3 kilograms, M1 equals 1 kilogram, theta 1 equals 30 degrees, theta 2 equals 45 degrees. Coefficient of kinetic friction between block 2 and the incline is 0.25. The coefficient of kinetic friction between block 3 and the incline is 0.15. And simple, we just, if you can refer back to the beginning of the video, you'll see the equation that I used, derived, if acceleration is caused by m3. So just plug in the value. And after doing the math on my calculator, using this equation that we derived earlier, I got acceleration equals 2.65 meters per second squared. Yeah, just using my calculator, plugging the values. And so now we'll move on to the second part of the question. It's a car on an incline, a banked incline. And so yeah, let's go over the theoretics of it, and then plug in some numbers. Alright, for this kind of question, is not with all the parts given to us and the length of this video so far, I just want to go over the main diagram that will really help you solve the question. And I'm pretty confident with this part of the unit. So it's just when you draw the incline, theta, it's the angle given to us. So here's your car, just going to draw a point, and so N, the normal force, is perpendicular to the incline like that, but mg is straight down. But now, if you want to break it up, so f of n's like that, the vertical component is fn is f of n times cosine of theta. Horizontal component inside the curve, which is important, is f of n sine of theta. So this is breaking down the normal forces. Sorry, this is breaking down the normal force on the incline, and when there's friction, also important. Force of friction, it's going to be acting. That's the incline like that. Force of friction is going to be acting parallel to the incline. Down, vertical component, f of f sine of theta, f of f cosine of theta. So, like that. And now, this is important. And cosine theta minus f sine of theta minus mg equals 0. That is saying so this is the force, and this is this is the normal force acting vertically, and cosine theta, and f of sine theta is the frictional force acting downwards, and then mg is just gravity. Since there's no acceleration like that, it has to be equal to 0. Like that. So that is simple. So that's just one equation that we want to use though. And then the main equation is n sine of theta plus f cosine of theta equals mv squared over r. Centripetal force. It's not a new force. We did not label it on the diagram. We don't put f of c on the diagram. Do not label f of c. Thus, we put it, it's part of the actual force acting inside. So n cosine theta is the normal force going like that into the curve, and that's the frictional force going into the curve. And then that's equal to the whole centripetal force, which is mv squared over r, and the radius is given. Yeah, the radius would be here. This is the radius. And the velocity would be either we had to find it or such, and just simple algebraic manipulation. So it's asking that we draw this free body diagrams, which we did, and we could plug in values based on this, but so the first question is asking us, the car moves at the largest speed possible for no slipping, and that'll be, we would solve for v squared in this. We'd be given the m, solve, given, usually given the angles, and that, and we would solve for v squared. And so that's equal to v. I'm not going to put in values now since the video is way over 10 minutes, but that's the theoretical equation that we want to use. So the square root of n sine theta plus f cosine theta times r over m, which will be the velocity with no slipping given the friction there. And you have to use the coefficient of friction given. And part 2 is asking the smallest possible speed for no slipping. So there'd be a range. It'd be the same thing, but it would be like a range for the velocity. And then the last question is asking the precise speed at which no friction would be needed. So that would be just making sure that the n sine theta is that there's no acceleration going up the slope or down the slope. So it has to be within that range given that we would solve for. And yeah, I'll just right now for the last part I'll just search some values that would be somewhat maybe used in these type of scenarios. And so lastly, I searched up some values that might be used in this situation. So theta 13 degrees, a radius of 150 degrees, or 150 meters, excuse me, and that would be here, the radius of the track, like that. Mass of a car around 1,000 to 2,000 kilograms is average 1,500, and then the coefficient of static friction between rubber and tires is around 0.7, and for a race car we want optimal amount of friction to prevent slipping as seen here, so that they could bank the curve without slipping up or down. But so that's it. Thank you, Mr. Roth, for letting us do these corrections. Sorry for my video going over a little longer, and thank you.